Okay, so this video, we've got some molecular geometry to talk about. And molecular geometry, it's going to go along with dot diagrams that we looked at the other week, so hopefully you spent some time figuring out how to draw dot diagrams and remember the term electron domain, because we're going to talk about those again too. And why are we going to spend time talking about the shape of molecules? Well, it helps to determine the polarity of molecules, which is going to be important to figure out. It helps determine the reactivity of molecules. The shape is also very important for biological systems like us, because a lot of the chemistry that goes on right in our bodies, we want it to be selective, and so shape plays a big part in how biological systems engage in selective chemical reactions rather than just like crazy random chemical reactions going on all the time. It's also important for understanding intermolecular forces, which there will be a video coming up. In fact, not just coming up, but the next video that you will watch that is up on Canvas in this same week. So getting into some molecular shape. This is the molecular shape chart that I have. Like it says here, yes, I will put this up on Canvas, so it should be in this module available for you. No, you will not have to memorize it. Hopefully I'll just print this out and you can have it. Hopefully I have remembered to do that by the time I see you. So drawing dot diagrams. All right, we're going to go from dot diagram to shape in only 34 short steps. So, get your paper and pencil ready. You might want several pages for all these steps. I'm just kidding. There are not 34 steps. This is going to seem like a long process the first time that we do it, but it is not really that terrible. So we'll do some examples here. And we'll start out with the great example, CH4, methane. So drawing the dot diagrams, remember that you start by drawing dot diagrams of your elements. There you've got carbon, 4 valence electrons, hydrogen, 1 valence electron. We're going to draw the diagram, right? Select our central atom, which in this case carbon, because carbon's there, it's a central atom. We got a hydrogen around here. All right, one single bond between the center and each surrounding atom that uses 1 electron from each of the atoms. Right, then we figure out if we need to put any unbonded electrons in. We don't. We count up, full octet, 1, 2, 3, 4 bonds, so that's 8 electrons. Great, full octet. So now what we look at here, we are going to look at electron domains, which, if you don't remember, right, that's any area around an atom that is occupied by electrons. So that includes bonds and lone pairs. So in this, we have 4 electron domains, right, because there's 4 bonds. So 1, 2, 3, 4 electron domains. Great. And then we look, are any of those electron domains lone pairs, which means a pair of unbonded electrons, which they are not. This has 4 electron domains, no lone pairs, so we look over here. We have number of electron domains on the side, right? I have labeled this graph or this chart. So we have 4 electron domains. Down here at the bottom, number of lone pairs. Oh, I just wanted to underline it. There we go. 0 lone pairs. So we look, 0 lone pairs, 4 electron domains. We have a tetrahedral shape, which draw kind of like this, tetrahedral. And we can put these fancy wedges and dashes in here, right? Which not doing a great job on here, but you get the idea. And so what the wedges and dashes mean, so you know, the wedges, right, these filled in wedges here, basically are meaning that that particular, whatever is there, like let's say, you know, each of these is a hydrogen, right? That hydrogen is coming out towards us three-dimensionally, and the dashes, right? The dashes here. Basically, that means that that is like going into the screen, right? So it's a way to kind of make these or represent 3 dimensions on a flat screen. And so that's really all there is to figuring out molecular shape from dot diagram. So let's try another one here. HCN. Again, we've got drawing our dots, 4 dots for carbon, 1 for hydrogen, 5 for nitrogen. And so then we start drawing. We've got carbon in the middle, 1 bond between each, and the extra electrons hanging out. So then we look, full octet, no full octet, right? Hydrogen's fine, carbon and nitrogen are not, right? Carbon only has 6 electrons, nitrogen 6 electrons. So we start taking electrons, right? We take 1 from carbon, 1 from nitrogen. We make another bond, and we check for octet. Again, not octet, right? Carbon, 3 bonds and 1 electron. That's 7 electrons. Same with nitrogen, all right? 2 bonds and 3 electrons. That is 7. So we have to make another bond. All right, we're going to take 1 from carbon, 1 from nitrogen, and make 1 more bond. And now, right, carbon, full octet, 4 bonds, 8 electrons. Nitrogen, full octet, 3 bonds, 1 lone pair, 8 electrons. Great. So then, molecular shape, right? We always look at the central atom for molecular shape. We look, it has 2 electron domains, right? There are 2 spaces around it that are occupied by electrons. 1 is here, 2 is here, right? All these bonds count as 1 electron domain. They're 1 area of space that is occupied by electrons, so they all count as 1. So we know we've got 2 electron domains. We look, are either of the electron domains lone pairs? They're not. So we go over here, we have 2 electron domains, 0 lone pairs. That is linear. So we have a linear shape for this one. Let's look at everybody's favorite molecule, H2O. So again, we're going to go through the process here, write out our elements, put in our valence electrons. Hydrogen has 1, oxygen has 6. This time we look, least electronegative or furthest from fluorine. Turns out that is oxygen. In this case, oxygen is the center. Despite the fact that it is neither furthest from fluorine or the least electronegative, because hydrogen, as we know from the rules, can never be in the center. So we have our hydrogen, our oxygen, we make 1 bond there, and then we put in any non-bonded electrons. We check, does everything have a full octet? Right, hydrogen is fine, just those 2. Oxygen, 2 bonds, 2 lone pairs, that makes 8 electrons, full octet. Great. So now we look. Oxygen, central atom. How many electron domains does it have? We have 1, 2, 3, 4. All right, we've got 4 areas where there are electrons hanging out. So we know electron domains. We go over here. We circle, if I can find my, there we go. We circle 4. And then we look, are any of those electron domains lone pairs? In this case, absolutely yes. 2 of them are lone pairs, right? So we've got 2 lone pairs. We look, 4 electron domains, 2 lone pairs. That is a bent shape. So water, bent. Let's do one more here. Take a look at one more. Iodine trifluoride. So we look, iodine, fluorine, both of them have 7 valence electrons. Great. Now, choosing the center, right furthest from fluorine or least electronegative, iodine fills both of those. It is further from fluorine than fluorine is. It is also less electronegative than fluorine because everything is less electronegative than fluorine. So we put iodine in the middle. We put our 3 fluorines here. Put our 1 bond to each. And then we fill in the electrons that are not bonded. Right? So for iodine, we have 2 here, 2 pairs here. For each fluorine, we have 3 pairs. Okay, then iodine being our central atom. Oh, wait, we look to make sure everything has a full octet. All right, each fluorine, 1 bond, 3 lone pairs. That makes 8 electrons. Great. Iodine, though, right? Remember, we've got 3 bonds for 6 electrons, 2 lone pairs for 4. That makes 10. But iodine being in row 3 and beyond, it can be hypervalent, so it's fine as long as it's the center having more than 8 electrons. So we're good. So then we count electron domains around the central atom. 1, 2, 3, 4, 5. So we have 5 electron domains. We can go over here, 5. Then we look, how many of them are lone pairs? We have 2 of them that are lone pairs. All right, so we look, 2 lone pairs. So 5 electron domains, 2 lone pairs, T-shape. All right, very creative name. T-shape. So that is how to find the molecular shape. Now, let's take a second to talk about polarity. So symmetry and polarity are pretty much completely linked in molecular geometry. So molecules that are symmetrical are almost always nonpolar. Molecules that are not symmetrical are almost always polar. So symmetrical molecules can be nonpolar even if they contain polar bonds, right? Remember when we talked about polar bonds, you can have a nonpolar molecule that has polar bonds in it, right? Polarity and shape, no different, right? Polar bonds in a molecule does not mean that it's going to be a polar molecule. So there are some shapes that are never symmetrical, right? Bent, trigonal pyramidal, seesaw, T-shape, square pyramidal. They are never going to be symmetrical. They just aren't. Then there are some shapes that can be symmetrical. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar. All right, I say they can be symmetrical, so we're going to have to take a look at them on an individual basis. But there is one rule that makes it a little easier. So those shapes, right, the ones that can be symmetrical, are always symmetrical when all elements bonded to the central atom are the same, right, or identical. All right, so like that first one that we looked at, methane, CH4, carbon, all the spots around it were filled with hydrogen. That is a symmetrical molecule, right, because it was tetrahedral and all the elements around it were identical. So otherwise, you're going to need to use your best judgment. Do the best that you can. I realize looking at this chart, trying to picture it in 3 dimensions is not easy for everyone. So do the best and see if you can figure out if things are symmetrical when they're not, when they don't have all of those bonded to, all the same atom bonded to the central atom. Okay, so some polarity examples here. We'll continue on with our dot diagram and molecular shape extravaganza here. So the first one we're going to start off SF4. So we've got sulfur, 6 valence electrons, fluorine, as we discussed in the last example, 7. So here, again, right, sulfur is going to be the center because it's less electronegative than fluorine. It is also further than fluorine, or further from fluorine than fluorine is. So we've got 4 fluorines around sulfur. Great. 1 bond to each of these, and then putting in any unused electrons, which in the case of sulfur is 1 pair. In the case of each fluorine, that's 3 pairs, 6 electrons, right? Because remember that each bond has 2 electrons, 1 each from the atoms that are engaging in the bond. So then we look, does everything have a full octet? We look at fluorine, 1 bond, 3 lone pairs, great, that is 8 electrons. We look at sulfur, 4 bonds, 1 lone pair, that's 10 electrons, but again, sulfur can be hypervalent because it is in row 3 or beyond. So then we count up electron domains around sulfur, 1, 2, 3, 4, 5. Great, 5 spaces where electrons are existing. And then we look, we have 1 lone pair. So we're going to make 1 lone pair. So 1 lone pair, 5 electron domains, that is seesaw. That is on the list of things that will never be symmetrical, right? And if we look at this, we will know why. All right, so if we've got our sulfur, our fluorines, all right, you might think that, like, okay, this looks like it might be symmetrical, but it's not, right? Because you've got this 1 lone pair hanging out over here, and these fluorines hanging out on this side, right? So it's not symmetrical. You're going to have your partial negative there, your partial positive here, right? It's going to be in that direction. So there you go. It is polar. It is not symmetrical. Electrons on one side. So the next one we'll take a look at. Xenon tetrafluoride. So I know that I've said noble gases won't engage in bonding. However, xenon will occasionally engage in bonding, and it is considered to have 8 valence electrons. So, right, again, fluorine never the center, so xenon ends up in the center. We have 4 fluorines here. We draw 1 bond to each and then start filling in any non-bonded electrons. I'm only going to do this one fluorine here because I'm tired of making so many dots, and they will all have the same number. So if we look at fluorine, right, full octet, 3 lone pairs, 1 bond, that's 8 electrons. If we look at xenon, it has 4 bonds plus 2 lone pairs, right, and that actually gives it 12 electrons, right, but because it can be hypervalent, it's completely fine with that. So then we start counting up electron domains. We've got 1, 2, 3, 4, 5, 6 electron domains, right? So we're down here, 6 electron domains. We look, 2 of those are lone pairs, right? So 2 of them are lone pairs. Square planar. So this falls under our list of things that can be symmetrical, right? When everything around the center is the same. So here's the thing though, everything around the center is not the same, right? But if we draw, if I can draw this, oh, come on, cooperate. If we draw it like it's shown here in the diagram, right? We've got fluorines hanging out here. We've got something like this. It turns out this is symmetrical, right? Because even though we don't have everything in the same, all the same stuff around here, right? We do have this situation where basically no matter which way you turn this, it's still going to look the same, right? And so this one is symmetrical, this one non-polar. So hopefully this is making some sense at this point. We'll do one more here. CH2Cl2, which in the land of organic chemistry we call dichloromethane. It is a very common solvent to use in organic chemistry. It smells a little weird, but it dissolves a lot of stuff pretty well. So there we go, dichloromethane, or you know, for those of you in the organic chemistry lingo, right, some dichlor. And we're going to put our elements around here, right? 1 bond to each. Put in any electrons that are not bonded. And then we look for full octets right around the chlorines. We have 1 bond, 3 lone pairs. Great, 8 electrons. Hydrogen is fine with 1 bond. And chlorine, or sorry, carbon in the center, 4 bonds, 8 electrons. Great. So then we look, central atom, number of electron domains. We've got 1, 2, 3, and 4. All right, so we know we're over here. 4 electron domains. None of them are lone pairs. Oh, I missed the 0 there. So we've got tetrahedral. Now, the question is this symmetrical? Depending on how you draw it, right, you might think it's symmetrical, because if you draw it like this, that looks pretty symmetrical. But if we draw it like it is here, I don't know why this doesn't want me to fill stuff in. Right? We've got Cl, even if I put the Cl on the other side here like this, right? We've got the same way I drew it over there, but if we look, right, we can see that 1 chlorine's going into the screen, 1 hydrogen's coming out of the screen. These 2 are kind of on one side, this is kind of on another. This is not symmetrical, right? Because it's really not going to look the same when you twist it. Because here, right, I haven't actually changed how anything's connected, right? So if I draw it another way, right, like if I draw it where we've got both the hydrogens like this. Right, we've got one chlorine here, one chlorine here. It doesn't really look symmetrical anymore, but I haven't done anything to change the molecule. I've just changed how I'm representing it in space. It's like I took it, grabbed it, and turned it in space. So, right, this is where it gets a little complicated to see, and it becomes much easier if you can easily visualize things, flat things on paper or screen in 3 dimensions. If you can't, I know a lot of people struggle with that. Sometimes it's a little tougher to see, but this, right, it is not symmetrical, it is polar, and that's how this works. So things to remember before we wrap up here. Right, the shape of a molecule is determined by the number of electron domains and how many of those domains are lone pairs. Whether or not a molecule is symmetrical can help determine if it's polar or nonpolar, and that molecules again can have polar bonds and still be nonpolar molecules. Okay, so there is some practice on this. Go try that out. If you've got questions, let me know, and I will see you in class. Have fun drawing.